Okay, good afternoon, ladies and gentlemen. Welcome to I²CNER seminar. So, I am I²CNER from Thermal Science and Engineering Division. Today we have two distinguished speakers in heat transfer engineering. So, first speaker is Professor John Laws from the Queen Mary University of London, United Kingdom. So first I'll briefly introduce him. So Professor John Laws has been a full professor at the Queen Mary University of London since 1985. And he is a fellow of UK Institution of Mechanical Engineers and also the American Society of Mechanical Engineers. So he is also a member of UK Heat Transfer Committee and UK Heat Transfer Society. And he's stayed with a sabbatical as in MIT and US and naval postgraduate schools and the University of Tokyo and Kyushu University. And he also served as a visiting professor at Kyushu University too. And his main research interest is the field of condensation heat transfer. So he published over 300 technical and experimental, theoretical and experimental papers. And also he served as an editor of International Journal of Heat and Mass Transfer and also the other journals. So today's his talk is Dropwise condensation, and he is I think the only person who can tell the whole story of condensation. Okay, so please start, John.
Thank you, Professor Takata. Is this microphone okay? Unfortunately, I tend to speak very quickly, so I will try to speak slowly, but as I forget, I will speak more quickly, unfortunately. I don't know if my English is fairly clear now. Okay, let's hope so. Now, dropwise condensation has been studied now for around 80 years, but quite recently there has been a flurry of activity. More work is being done. Particularly in relation to what have been called superhydrophobic surfaces, surfaces with a very large contact angle. I shall say a word or two about that, but I was told that I would be speaking probably mostly to students, and what I shall do, although Professor Takata said, I know all about dropwise condensation. What I shall talk about today is mostly my own PhD, which was completed in 1964. First of all, these are a few quotations, not specifically to do with dropwise condensation, but things that I feel I want to tell people. Recently, there has been an enormous growth in publications, not only in heat transfer, in all fields. Much of it is not read by anybody. Everybody has time to write papers, but few to read them. These are not my quotations, these are from other people. Much of what is published has not been carefully reviewed and is not read, or only briefly scanned so as to cite and placate potential reviewers. I'm speaking now as a researcher, as a reviewer, and as an editor. Many present-day authors are not aware of much of what has gone before. Work is unnecessarily repeated, often with errors. The zeal, enthusiasm for quantification of what passes for scholarship, number of papers, citation index, etc. Metrics such as impact factor and citation index are not reliable, in my opinion, indicators of quality of research. In the old days, The Journal of Heat and Mass Transfer, much less than a centimetre for 1 month when you see it in paper. When you see a month in paper now, it's about so thick. Most people don't see it on paper. It's in the sky, it's in the computers. But as I'm saying, a lot of it is not read. Now, talking in general, before I start talking about my thesis, these are key points in dropwise condensation, which I think are unquestionable. In my mind, these are absolute facts. A clean metal surface will be wetted and will not give dropwise condensation. You need to apply some kind of agent which will make a metal surface not wetted and give dropwise condensation. The heat transfer coefficient, many heat transfer coefficients have been published over a very wide range. I'll talk about that later. The heat transfer coefficient is roughly 20 times film condensation at atmospheric pressure and around 10 times at power station pressure. So, and we have the potential to reduce the overall condenser size if we could go to dropwise condensation, and people have been trying for 50 years without success. We could reduce the size of a condenser by about a third. Now, if that condenser is in a submarine or in a ship or something, the size is very important. Accurate measurements. Many investigators have reported erroneously low heat transfer coefficients due to the extreme sensitivity to the presence of air and insufficient accuracy in the measurement of the very small temperature difference. That's between the vapor and the condensing surface. Accurate measurements show that the heat transfer coefficient increases as the temperature difference increases, which is rather unusual. As you increase the delta T, temperature difference, and you increase the heat flux, the heat transfer coefficient increases, and it decreases with decreasing pressure. There are theoretical reasons why that should be. Heat flux up to 10 megawatts per square meter have been obtained for steam before the onset of transition. Analogous to the transition of nuclear boiling to film boiling, at a high enough heat flux, you will have a transition from this. Even the non-wetted surface will form a complete film, but not until 10 megawatts per square meter. Theory, 1966, co-author me, is in excellent agreement with the accurate data. The main problem, which remains to be solved, is durability. Nobody has succeeded in making dropwise condensation under industrial conditions last for long enough. And by long enough, that means maybe tens of years. It would be a long PhD if you were working on. I can't think of any way of doing accelerated tests. And no, but there, in the UK in the 1950s, our National Engineering Laboratory ran tests for maybe some thousands of hours and maybe 1 year, but nobody has had the confidence or courage to design a condenser for dropwise condensation, because if after 2 years it reverted to film condensation, the condenser would be a third too small. The efficiency would go down, the condenser pressure and temperature would rise. Now, there are recent measurements on these so-called superhydrophobic surfaces generally give lower heat transfer coefficients than smooth surfaces, despite what the people who write these papers say. That's what, this is a picture from my thesis, 1966. This is what dropwise condensation looks like. This is 5 centimeters square. This is the non-wetting agent, which was developed during the 50s by our National Engineering Laboratory. These droplets, they fall, they don't come down the surface like that, they come like that. This is at a lower heat flux, this is at a very high heat flux. At this heat flux, if you saw a film, a movie of it, it's blurred, you can't see it. The droplets are doing this. So that's what dropwise condensation looks like on a smooth vertical surface. From this picture, this was taken out of the condenser and carefully removing the droplets here and taking the photograph to demonstrate that the contact angle on a smooth surface is approximately 90 degrees. That's a picture, a faded picture from my thesis before computers. This is the heat transfer coefficient, this is the heat flux. These are the measurements of different people which existed when I started my PhD. And my PhD objective primarily was to find out why there is this big discrepancy. Some people find it goes up and down, some people find it goes up, some people find it came down. And if you realize these are smooth data, cloud of points there, cloud of points there, cloud of... The whole picture was a cloud of points. And my supervisor said, your job is to find out why this is and to produce the definitive correct results. Now, these are data for steam at atmospheric pressure. Most of them mine, delta T against, this is the temperature difference between the vapor and the condensing surface. This is the heat flux. There's quite a lot of data here. These are the more accurate data. Other people have found stuff all over the place. I should mention that this Tanner, this was done at one of our national laboratories near London. They were producing results with much bigger delta T's up here until I went to see them. I spent a day with them, and a month later they produced results in here. This is MIT work. I spent a year at MIT, I think Professor Takata said. When I went there, they were producing data up here. And after a month, they came down into here. There are reasons for this, which I hope I may have time to talk about. Now, that's a picture now coming up to 1998. Some of these are the ones you saw on the earlier slide, and some of these are some more. And in this range is the truth. I have no doubt whatsoever this is the truth. Much, much lower delta T's than most of these, which means much higher heat transfer coefficients. In fact, I should say this is the correct and logical way to plot. This is the variable which you control by controlling the coolant flow rate or the coolant inlet temperature. And this is what you measure. You measure the steam temperature and you measure the surface temperature. Most people plot the reciprocal, this one divided by this one, which is the heat transfer coefficient, against this one. This is the dependent variable, and it can be very low. So plotting its reciprocal can give you large scatter. So this is the way I always plot the data. Here is the truth. This is interesting. This work was done in Japan by Professor Tanasara and Utaka, and they extended this to the next room. This is 10, this is 2. So 5 times over there. Had I plotted all of that together, all of this bunch would be in the corner. So I just it follows this same pattern right out to 10 megawatts per square meter. This was done in 1983. Now, I'll come back to this later. This is the region containing the new data, or the recent data, for the so-called micro-nano structured superhydrophobic surfaces. Sounds very interesting and exciting, but as you can see, the delta T's are all much bigger than these. Heat transfer coefficients not so good. Critical considerations for accurate measurements. The surface temperature must be measured with an accuracy around 0.1 of a Kelvin. The results are extremely sensitive to the presence of a non-condensing gas, or air typically. Only a few parts per million will completely depress the heat transfer coefficient very significantly. And this is a thing which people have not commented much. Once you've got rid of the air problem, the non-condensing gas problem, I found that the heat transfer coefficient slowly rises over 2 to 3 hours. I was not using a data logger, they didn't exist. I was balancing a bridge and watching a spot, and it took to do a set of readings, took me about 20 minutes. And then I went back to the beginning to repeat, to make sure everything was right, but the surface temperature had gone up a little bit, only a tiny bit. So I repeated again. I thought that first bit might be a little bit of error, but it had gone up again, and again, and again. It takes around 2 hours. I'll come to that later. Temperature measurement. When I started my research, the first thing my advisor, Professor Lefebvre, said, go to our National Physical Laboratory for a week or maybe 2 weeks and learn how to measure temperature accurately, properly. So you need a reliable standard, you need good equipment, and you need good technique. You can't just buy thermocouples and stick them in and that will give you the answer. There's much more to it than that. For instance, thermocouples should run along isotherms near junctions. You should take care to avoid direct sunlight on your equipment, your apparatus, any connections. And the leads from the thermocouple, any leads, in this case we use very fine wires, but you need to have more substantial leads to your instruments. All junctions of any materials, even copper to copper, 2 different kinds of copper joined together. If you put a match on the junction, you will get a very tiny EMF, but significant. Now this was this kind of setup that I use. Here is the steam, here is the test plate. Make arrangements, good insulation, so that you have essentially one-dimensional conduction. These thermocouples, these are thermocouple holes. The thermocouples are located to within 0.1 of a millimeter. The surface temperature is found by extrapolation. The steam temperature, when you've taken all the precautions I mentioned, you can measure to about, that's about the best you can do, plus or minus 0.03. And that will give you an uncertainty around 0.1 Kelvin. Probably should be better. And the heat flux from the slope will be within about 1%. These are the sort of accuracies you need. And this, another picture from my thesis. These are different cooling water flow rates, different heat fluxes. This is temperature against distance from the surface. As the cooling water flow rate went up, the heat flux went up, and these lines are steeper. This is a copper plate. If you take any one of these points, the maximum deviation from the least square straight line was 0.05, if you look at all of them. And if you look at the transverse direction, the maximum deviation was 0.03. So using these, we can estimate the error in the surface temperature will be better than 0.1 of a Kelvin, and the slope, or which will give you the heat flux, is better than 1%. Not easy. Having done all that, I started to try to take some measurements. This is the temperature of the thermocouple nearest to the steam side. It was a little bit less than 1 millimeter. And this is what it was doing. With the air concentration, less than 5 parts per million. No point in measuring this to better than 0.1 when it's fluctuating by 1. So I surmise this was I thought, I was pretty sure, this is the build-up of air close to the surface. Where the steam is removed, the air builds up and you get a boundary layer. And this was the technique I used. I brought in a vent and extracted some steam from here. In this particular case, I started off with 1 centimetre distance here. And that's what happens. With the vent open, almost no fluctuations, and the temperature is risen by more than a Kelvin. The faraway concentration is only 0.5 parts per million. Very significant difference. This shows the effective venting rate. If you don't vent anything at all, your temperatures are up here. When you start venting more, the temperature difference comes down, and fortunately, you have a horizontal region. If you vent too strongly, you disturb the drops, and the surface temperature goes up, and the delta T goes down. But the important thing is you have a region where your vent is not affecting the result, but it is removing the air, boundary layer. And we experimented with different venting rates and different positions of the vent so that we could always get data in this region. Now, the time to reach steady state, this is after the air problem has been removed. It takes, in 2 hours, the heat transfer coefficient, this time I'm plotting against time, comes up here and then continues at a steady state. But if you are taking your data with a data logger, you may not notice this. But if it used to take me something near 20 to 30 minutes to get 1 point. Then to repeat that, I found the next, it was here, and then here, and then here. It took me 2 hours, this may easily not be noticed if you're data logging. See, between each one of these points is something like half an hour. If you're looking at an output from a computer, it looks steady. But if you look long enough, you'll find it's gone up. I haven't seen anybody else mention this, but you can see the difference in heat transfer coefficient from about 0.17 here up to about 0.25. Very big difference. If you take your data too early, you get too low heat transfer coefficients. And these were the final results that I got. This is delta T plotted against heat flux for 4 different promoters. These were investigated and developed by our National Engineering Laboratory in the 1950s, and I used all 4 of them. You can see clear differences between the promoters. And each set of results was done on 3 different days. So this is very repeatable. Not much difference between these 2 promoters. That one's a little bit worse, and this one is worst of all. But all of this is film condensation. You can see what a big advantage. Sorry. What's the jump? Yeah. If we transpose these lines into the usual plot that other people do, which I think is not logical, to plot heat transfer coefficient against either heat flux or delta T, those lines become these. The heat transfer coefficient is increasing with delta T or Q. This is film condensation decreasing, and a very big difference. Now, these data were the first accurate measurements, and they show the heat transfer coefficient increasing with increasing heat flux. I don't think I've ever seen this mentioned anywhere except in my papers. Wenzel, working in Germany, actually the work was done during the war, during the Second World War, but not published until 1957. Now, these are old-fashioned units. If we take this line and transpose it to the units I was using, these are Wenzel. See, fits in quite nicely. These promoters are these. Wenzel used oleic acid. Clearly fits into the pattern. Summary, required accuracy should be at least this. The effects of air, even minute concentration, need to be avoided, and the time dependence need to be considered. Now, I say a few words about dropwise condensation theory. This, again, in those days, if you published something in an international conference, that was regarded as pre-publication. You weren't allowed to publish it in a journal. It was all, so this theoretical work, based on my thesis, was never published in a journal. However, let's talk. It's, in my opinion, it's essentially correct, not surprisingly. We took, although, as you saw the photographs of droplets doing this and droplets growing and coalescing, if you could see it, we decided to take a quasi-steady approach. Let's calculate the heat transfer through a single drop and combine that with a time-space average drop size distribution to get the average heat transfer for the whole plate. So two parts to the theory: the equation for a drop of given size combined with a steady drop size distribution. This is the equation for heat transfer through a single drop. This is your delta T. This is the amount due to surface tension and surface curvature that you have to cool the vapor below its normal saturation temperature before it will condense. So you lose some of your available delta T. This is important when this is very small. And the smallest droplets are of nanometer size, so this becomes significant. And in the end, it defines the nucleation site. When this is equal to this, nothing can condense, so it has to be bigger than that. This resistance is due to conduction in the drop. This is thermal conductivity. This is the radius of a hemispherical drop, and this is an unknown constant. Because of the extremely high condensation rate on the small drops, very small drops, the interface matter transfer resistance, so-called, is important. There is a temperature drop within a few mean free paths in the vapor, and this is an expression for that temperature drop based on kinetic theory of gases. In most applications, this is negligible, but in dropwise condensation, it plays a significant role. In fact, because this term, this is the specific volume difference between the gas and the vapor. Effectively, this is the specific volume of the vapor. At low pressure, this gets very large, and this term becomes important. And this explains why the heat transfer coefficient goes down as the pressure goes down. This is the thickness and thermal conductivity of the promoter. We've introduced now two constants. This constant, if we modeled the drop as we have a hemispherical drop, to get a rough idea of what the maybe not so rough idea of what the heat transfer would be, if we modeled the drop as a cylinder with the same volume and the same base radius, then it will be one-dimensional conduction, and K1 would be 2/3. K2 is simply the ratio of the base area of the droplet to the curved surface area. For a hemispherical drop, that would be a half. Now, in the original paper, maybe it wasn't a good thing to do, confuse people, we combined this into here, and that gives you a different constant, which we called K2, which would be equal to K2 naught if this were negligible. But that's basically the equation which comes after my thesis. Now, this was entirely due to my advisor, Professor Lefebvre. By considering ideas about packing of circles on a plane, he came up with this idea for the mean size distribution. F is the fraction of area covered by droplets with base radius greater than r. And this is the maximum drop size. So, and this is another constant, n. So you can see, if if R equals R max, this will be 0, which tells you that no area is covered by drops bigger than the biggest, which is obviously true. If this went down to 0, this would be 1, which means all the surface would be covered if the drops by droplets greater than 0. So this has got the right overall boundary condition, but it introduces n. This implies this. This is the fraction of area covered by drops in the size range R to R plus dr. Then, to get the heat flux from the plate, we have to integrate the heat flux through the base of a drop times the area covered by the drop, from the minimum size to the maximum size. The minimum size is given by the sometimes called Gibbs-Kelvin. This is due to surface tension. A drop smaller than that would evaporate. The maximum drop size, we use dimensional analysis, which introduces yet another constant, K3. Now, so we've introduced K1, K2, now K3, and N. And at the conference, it was in Chicago in 1966, at that time, in that conference, we didn't present our papers. There was a rapporteur who discussed 4 or 5 papers. And the rapporteur at that time was Peter Griffiths of MIT. And he was fairly complimentary, but he said, if you have 4 unknown constants, you can fit anything, which is true. But all of our 4 constants can be closely estimated without reference to the heat transfer data. We chose to use the heat transfer data as we thought would give us better values. But they weren't freely adjustable. Well, they were, but they came out to be very close to what we could have estimated. In fact, almost exactly. See, I jumped ahead of myself here. If we look at, these were the pre-estimates. The constant K1, based on that simple model, would have been 2/3. K2 would be dependent on the promoter. But if the promoter resistance was 0, it would be 0.5. N, Lefebvre, based on his theories of packing of circles on a plane, thought it ought to be around 2, but he wasn't sure. We found, when we did the curve fitting, we found it was 3, was much better. And this was later verified both by experiments in Japan and America, nothing to do with me, taking microscope photographs and painstakingly measuring the size distribution. I'll show you a graph in a minute. And these were the value, if the maximum drop size were taken as a millimeter, which you can see with your eyes round about that, then K3 would be 0.4. Then we fitted our theoretical result to those data I showed you earlier on, at atmospheric pressure, which were I considered the most accurate data available, and came up with these, almost like this one the same, this one the same, this one 0.5, this one, as you saw from the measurements, depended on the promoter. If the promoter layer had no resistance, this would be 0.5. And we found it varied between promoters between 0.5 and 2. N we found to be 3 by curve fitting the data, and this 4. Almost exactly the same. This is just to demonstrate. This, again, is the same equation expressed in a different form for the size distribution. This is the number of droplets in the size range R to R plus dr. It follows from this. If you take n equals 3, this is this line with n equals 3 here. These were the measurements done in Tokyo and in Boston, nothing to do with me. And this I did with a colleague, also at MIT, theoretical work later. All of these are later. The theory was published in '66. This theory, not based on heat transfer, was 1974. These data 4 years after the paper was published, and these data 7 years after. There's not much doubt that this is a correct interpretation with n equals 3. Going back to the equation I showed you before, this is the atmospheric pressure. This is the theory with those constants, and these are the accurate data. This is the same graph with all the other data. This is all mostly affected by air and sometimes inadequate measurement, well, mostly, in my opinion, inadequate measurement of the surface temperature. All of them better than film condensation, which is here. So for a given delta T, all of these give a bigger heat flux, but not as big as these. And in 1983, Professor Tanasawa and Utaka, using liquid nitrogen as coolant, extended this range, as I said earlier, up to 10, right over there somewhere. And it fits along this same trend. These were data taken in 1970 in our lab for different pressures, from around atmosphere to 1/10 of an atmosphere. The theory, without any changes of any kind, fits these data almost perfectly. These are the same scale, so this line up here would be up here. Clear effective pressure. And these were data taken by Tanasawa and co-workers in Tokyo, 1974. This time, they varied the maximum drop size using different methods, changing the inclination of the surface. They used a high vapor flow over the surface. They rotated the surface, all to measure the maximum drop size, to change it, to vary it. And the theory, without any change, almost 8 years, this was 8 years previous to this data, fitted it without change. Closing remarks on the theory. Very accurately predicts measurements for which due care has been taken. It predicts the magnitude. It predicts the dependence on delta T or Q, all the way up to 10 megawatts per square meter. It predicts the dependence on pressure. It predicts the dependence on maximum drop size. This is a little mild annoyance on my part. I see many minor modifications of this theory, unnecessary, I say. Usually the incorrect attribution, because this 1966 paper was in a journal. Young people nowadays, if they can't find it quickly off the computer, it doesn't exist. And sometimes with no attribution. Some investigators purport to have invented it themselves. Now, let's talk about the super high. This is the more recent work. As I said, much poorer heat transfer coefficients, much higher delta T's. It's all in this range. Now, if we considered a hypothetical case of a smooth surface with very large contact angle, you only get heat transfer through this small base. Here, the larger area, you've got convective heat transfer between a subcooled vapor and the surface. Very tiny heat transfer here. These surfaces are essentially adiabatic, and the heat transfer is only going through here. So we would expect such a surface to perform badly from the heat transfer point of view. Now, this is my idea of what it's an idealized microstructured surface. These are micro or nano grooves. I think the droplets are in fact like this, almost hemispheres, and here's contact angle 90 degrees, and this is what your eye sees. Very big drop. This is a nano dimension, or certainly a micro dimension. So this is the only one you see, these great big drops, but this is what happens. It's possible that due to these grooves, you could get more area and perhaps some enhancement. But of course, when I first read these things, it talked about micro-nano surfaces as if they were responsible for the superhydrophobicity, as they call it. However, reading carefully, they also need a promoter, which they called by a different, they didn't call it promoter, they called it functionalizing agent or something, which baffled me. But you need a non-wetting agent, just in the same way as for a smooth surface. Now, unfortunately, what happens as you increase the condensation rate, the regime switches to this. This is a stable contact angle. The grooves are filled, and you've got a much reduced area with dropwise condensation on there. Flooding occurs, and the heat transfer coefficient falls at this sort of heat flux. Tanasawa went up 50 times higher than that on a smooth surface before transition to film condensation. Another factor of the microstructured surfaces, droplets are observed to spring away normally. I can't go into the theory of why that happens. Instead of sliding down the surface, as in the case of a smooth surface, the biggest drops jump away. And that has been claimed to be a good thing, to improve the heat transfer. But if these droplets spring away, you don't get this cleaning effect. These falling droplets, as I said, very, very fast, are sweeping the surface clean for new nucleation, new condensation. So I would expect, if the droplets spring away, that will be a negative effect. You'll have worse heat transfer, not the reverse as claimed. Now, looking at durability. This, as I said, this is the main outstanding problem in dropwise condensation. Structured surfaces also require a non-wetting agent, which is not always made clear, not to me at least, in the same way as smooth surfaces. So there is no reason to think that the structured surfaces should be any more durable as far as dropwise condensation is concerned than smooth surfaces. There is no reason to think, and so far no evidence to show, that structured surface should give more durable condensation. And in conclusion, and I've got a bit of time, I can show you something else after. All the important work on dropwise condensation has been overlooked in recent years. That's all the stuff I've been telling you about. Many of these more recent investigators appear not to know about it. I think the accuracy of some of the recent work is questionable. Nanostructured surfaces offer no advantages for dropwise condensation heat transfer, in my opinion. They may have other usefulnesses. They may keep the windshield clearer or something like that. But as far as dropwise condensation heat transfer is concerned, in my opinion, they have no advantage at all, despite the fact that many investigations throughout the world have been done on this. The importance and significance of structured surfaces for dropwise condensation has been exaggerated. This is the main problem, durability for any kind of surface. Difficult to know how to work on this, but this is a problem which needs to be addressed. That was where I was going to conclude, but I just wanted to show you one or two other slides. We did some experiments also on inclination. This was our apparatus. Normally, this was not here, and this was vertical. Here was the test surface, and by using this flexible tube, we could rotate this in both directions. And this is what it looks like. These are two different heat fluxes. This is the droplets facing. That's the surface almost horizontal, just 5 degrees from horizontal. This is facing downwards, hanging droplets under here. That's what the picture looks like. That's at a higher heat flux, that's at a lower heat flux. And these are the heat transfer coefficients that you get. I haven't seen anybody measure this, and maybe it's not too important. This is a vertical. Not surprisingly, the heat transfer coefficient is best for a vertical surface. But as you go in the direction of hanging droplets, prone, this way, the droplets under here, interestingly, there's a second maximum, not at the same place precisely. For these are two different heat fluxes. For one heat flux, it's here. For the other one, it's here. Now, this was done many times, maybe 50 times, different heat fluxes. In every case, we got this second maximum here. Just to show you how difficult that is, these are the corresponding differences in temperature between the vapor and the surface. See, from this little minimum here, there is only 0.2 kelvins lower here than here. So you've certainly got to be measuring with a precision better than 0.1. Here, the difference between this minimum and this minimum is only 0.1. So it's not difficult to see why this has not been reported before. It needs extreme care and accuracy to do this. I was just emphasizing that point. And I think I'll stop there. Thank you.